Thank you very much, Professor Jene. And thank you for your interest in this presentation, where some of you may think, but that's a stupid subtitle, more intelligence or more sensing. Because if you've read attentively the announcement, then you would have seen that the authors claim it is obvious that one has to integrate. It is obvious that you have to combine smart acquisition with smart image processing. Well, let me admit, I'm a burned child. 30 years ago, when I was young, optical signal processing was all the rage, because the promise was, we will do optically, we will use photons for all the things that are so expensive to do. I see somebody with gray hair nodding, and the reply was no. The advantage of processors, the advantage of silicon-based processors, they grew so fast that all the optical processing disappeared. So my job really is to take an honest look at, are there really applications where if you knew more about the fundamental properties of photons, you could generate more insight, more valuable insight into a scene than just acquiring it with an ordinary camera and then applying all sorts of massive number crunching processing. Does this exist? Okay, let's check. I'm going to do that in two installments. First, I'm going to look into the properties of individual photons. So if you look at one photon, what you can find about it with physical means is, what is its wavelength? Indeed, one photon, you can find out precisely what is its wavelength. Then, what is its wave vector, or in ordinary language, under which angle of incidence is it appearing on the camera? The polarization, you remember this, its time of arrival, or even magnetic field, you'll be surprised. Then there are other properties where it's not sufficient to have one photon. You need bunches, you need groups of photon. And that's the spectral distribution. That's a temporal modulation. You cannot modulate a single photon. It's either there or not. Coherence, correlation. Unfortunately, I won't have the time to talk about these quantum aspects of light, although I'm really inspired by the possibilities, for example, of heralded photons. If you don't know what this is, and if you're curious, ask me during lunch. And I'm going to cover this one, corner. What happens if you have, if you know the time of arrival of photons or bunches of photons to femtosecond precision? What can you do with that? So, let me start with a motivational slide. Let me start with an everyday experience, the perception of polarization. This experience, this everyday perceptive experience of polarization is an everyday experience of her, is an everyday experience of him. Oh. You should not underestimate Professor Jene. And actually, you should not underestimate yourselves. You're going to see that almost all of you are sensitive to polarization. I don't lie. I'm going to demonstrate that to you. But before, let me explain how this all came about. Many of you know that bees are polarization sensitive. Actually, Professor Jene used the image of a bee to illustrate one of his slides. So, indeed, this has been researched extensively. So I was surprised to learn that only in 1986 the nature of this polarization sensing was elucidated much more clearly. And what people found out is that bees, they mechanically scan the sky. So that's not like a color camera. They have to do some mechanical scanning. Okay, now you may think that, oh, this is quite a recent development, and therefore the question whether we human beings are also polarization sensitive, that's also quite a recent question. Not so. The fact that we are polarization sensitive was discovered for the first time in 1844. The German Wilhelm Karl von Heidinger found out that actually most of us, we are polarization sensitive. We can perceive, almost all of you can perceive polarization. But, a big but, this is a sensing property you have that has a limit, and we can learn something from this limit. Because as many of your senses, it is AC coupled. Actually, this is a bandpass filtered sensing property, namely that if it's below 1 hertz, you don't perceive it. If it's more than 20, 30 hertz, you don't perceive it. So you can only experience temporally changing polarizations. So polarization change. Now, knowing that, can we exploit it and make use of it so that everybody now sees polarization? Well, if you read this, there is one obvious measure. So if we change the polarization pattern, you will see it. Actually, this works best in the blue, because there the contrast is highest. So I have now a blue screen, and I checked, it is not polarized. So the polarization direction of the photons coming from this screen, fortunately, it's very uniform. So polarization will be anything, right? And I've prepared this little toy for you. It's nothing but linear polarizer. I forgot to check which way it is polarized. Never mind. And thanks you to our coffee sponsor, Edmund Optics, they sold me that. Now what I'm going to do is very simple. I'm going to hold this in front of the screen. I'm going to rotate it, with watch speed, between 1 hertz and 20 hertz. And if you're close enough, you're seeing these Heidinger brushes with your own eyes. You see this yellow-blue pattern rotating. As soon as I stop the polarizer, you will stop seeing. So I cannot even show you a picture of what it looks like, only you can perceive it. Now, we shouldn't play for too long. This is a serious keynote talk. So for this reason, let's play during the lunch break. One thing I should mention. A friend of mine who made me aware of the Heidinger brushes, he said he was inspired by the bee. So apparently the bee is using some sort of scanning to perceive polarization. Now, knowing that rotation helps, he thought, what can he do looking at the sky and seeing polarization? What can our colleague, Professor Jähne, do so that when he's outside, he sees the polarization in the sky? Very simple. Do this. So next time you see Professor Jähne doing this, you know what he's doing. He is having an everyday experience. He sees polarization. Now you may ask, is this an important property, polarization? Can we use it technically? Yes, we can. And the main reason is that when light of different polarization is incident upon a dielectric, glass, lacquered surfaces, water, any liquids, then predominantly this polarization is emitted. Therefore, you can get rid of light, of reflected light, by having a polarizer that only lets light through in this polarization direction. And this was the big invention of the Polaroid founder, because he sold such cheap linear polarizers that made their way into sunglasses. And you see now how they work. So on the right, you see a picture, no polarizer. And what you see is reflected light from the surface you don't see beneath the surface. On the left-hand side, a polarizer was used, blocking the horizontal light, so now you see into the depth. Same thing is if you want to look through glass. So if you have a polarizer blocking horizontal polarization light, you see right into the car. Otherwise, you would not be able to do that. And if you don't have much light and you find it difficult to discern subtle parts of the scene, then the recommendation of these people in the reference is, hey, why don't you create images that show the direction of polarization? And this was done with a polarization camera, and you may ask yourself, oh, okay, is this difficult? No, not at all. It's very similar to the color mosaic cameras we all know for measuring what is the dominant wavelength. You just have over a small group of pixels, typically 2 by 2, different polarization filters. Normally, just these two, vertical, horizontal, are sufficient. They preferred to have these 4, so they have a 2 by 2 superpixel that generates this polarization image. Done. Okay? Now I should shift gears and talk about properties of photons that make them uniquely useful for understanding scenes. The example comes from my garden. This is not my garden, it's much smaller, but it also has strawberries. And I was impressed when I saw what does it mean that the strawberries are ripe. Well, they don't seem to change shape. They don't seem to change their morphology. The only thing that seems to change is color. I do not know, and actually I doubt it, whether you can throw so much image understanding at this scene and find out where are the ripe strawberries. As you know, we human beings don't do it this way. We do it this way. And if I switch back, it's really very hard, even impossible, to find out, is this a ripe strawberry, or is it a small strawberry that has ripened, or a big strawberry that is not ripe yet? In any case, this is much simpler, and that's why we do it this way. Now, looking at this picture or this picture, you may have the feeling, oh, it's wonderful, our sense of color. We see so many different colors. Actually, a trained colorimetrist perceives about 5,000 different hues. But it doesn't mean you have 5,000 different receptors. It is deceptively simple. You just have 3 types of receptors. And here are the sensitivity curves of the filters. You see a blue, a green, and a red. The blue is exaggerated by a factor of 20, so we're not so sensitive to blue. It's interesting that the red, it really has a hump here. So we do all kinds of image processing to come up with our perception. The important point is we don't perceive more than these 3 properties. So we can only say, we see that much red, that much blue, that much green. That's all we can do. And if you do a transformation of these three coordinates in other coordinates, you realize you can only perceive hue and saturation and intensity. That's all we can perceive. So we are quite limited in what we perceive, and still it helps us so much finding which strawberry to eat and which to leave on the ground. That's one of the famous chromaticity diagrams with which I like to remind you, although this looks so rich in color, just two coordinates suffice, and we know which dominant color the photon that is impingent has. Now, let's move on to another property that I don't know how to extract if I have a lot of image processing. It is finding out at which angle of incidence does a photon arrive. Strange. Is this something interesting, something useful? It is. And surprisingly enough, none other than Leonardo da Vinci made a picture where he wondered about that. This is the cover page of a publication by a colleague of mine, Ted Adelson, and he was writing about single lens stereo with what he called a plenoptic camera. And he also started his article with this picture from Leonardo da Vinci. And Leonardo just asked himself, if I know an object has a certain size, and then I'm moving my distance to the object, hey, the angle under which I see the object is changing. If the angle is small, the object is far away. If the angle is large, it must be close. That's where he stopped in his writing. I don't know about his thinking. Can we exploit this? Yes, we can. We can create a camera that measures, in principle, for each bunch of photons under which angle has this photon or this bunch of photons arrived. As I said, it was originally called plenoptic camera. These days, it's called light field imaging. And that's something you have in your electronic cameras. They are all supplied with this trick to measure how far away are the main objects, where do I have to focus, how does it work? So on a group of pixels, typically 3 by 3 or 5 by 5, you have a microlens. So these are the microlenses. Don't worry about microlenses. So for the moment, you can just replace a microlens by a hole. A pinhole, because actually a pinhole is a sort of lens, not very efficient, but the function is the same. So, the microlens is placed such that an object at a certain distance, typically a few meters, produces focalized light on one point. So, the group of pictures, of pixels you see, they are called RST in a 3 by 3 matrix, sees this pattern. So R and S and T, they see the light coming from one source, one point source in the object space, sees it in the same place. If, however, the object is nearer, then because of the properties of this lens, just imagine that it's replaced by a pinhole, then you see that, the R in the central pixel, in the central superpixel does not react. It's the R on the other side. And symmetrically, the T on the left-hand side. What this means is that if you look at a pattern in these different RRR subimage, and you compare it to the SSS subimage, and you see a shift between the two patterns, you know, the source of this pattern is not at the reference distance. And because you have not 2, but 3 or more, you can find out, is it closer to the camera or farther away from the camera? So with this trick, you can learn from each macro pixel, what is the color, because we're going to use color pixels here, and what is the distance of the object. And that's wonderful news. With one shot of a camera, you can create, for example, recreate pictures with very small depth of field, because you know from each small spot in the object plane at which distance is it. So you can create blurred images. Or if you want, you can create images like this one here. Everything is in focus, infinite depth of field with one shot. And at the same time, for free, the three-dimensional distribution, just by measuring the angle of incidence. Now, you can still buy it, but unfortunately, they are out of business. So there was this company, Lytro, and they produced these cameras. I don't know why, 2018, they just closed the doors. As I said, this company might be dead, but not the principle. In your electronic cameras, it's still used. Sometimes it's called the Honeywell principle, but now you understand this light field principle or planoptic camera principle has been around for a long time. It's very useful. It's used every time you use your electronic camera. Now, I started out with an everyday experience, polarization. You can perceive polarization. What about magnetic fields? And now you may object, but hey, you said you wanted to talk about photons. I do, because there are birds that perceive magnetic fields. They know which way they find themselves in a magnetic field. How do they do that? The point is, they don't have silicon chips inside capable of measuring the magnetic field. They see photons, but they see photons through a screen. And thanks to this screen, the magnetic field is converted into a polarization change. So a bird, and this is now simulated, we don't know exactly what a bird perceives, but from everything we know, a bird sees the sky in this way. The magnetic field is superimposed as a modulation of the light intensity. So before it was polarization. I don't know how they can distinguish between polarization and magnetic properties, but they see magnetic field. And the trick, you will be disappointed, is a very simple one. So this thin layer covering part of the retina of the birds is capable of rotating the polarization in function of the magnetic field. This is called a Faraday effect. The surprising thing is not that it exists. This has been known for a long time. The surprising thing is that birds, animals, living beings are exploiting this effect. Now I have a last application of watching one photon and exploiting its properties. It's the time of arrival. And you've seen such animations very often. It's just a reminder, if you know when a photon has been emitted and you can measure when does it arrive, you can deduce back, because you know the speed of light, about 3 × 10⁸ meters per second, you can deduce back this spot in the object space, this part of the object under scrutiny is at which distance. Now, this works well, but it has a problem. Remember, for the moment, I'm concentrating on one photon. Yes, it works with one photon. It's really true. But you have background light. And the background light is enormous. I made a quick calculation. Normal solar illuminance will create 10 to the 15 visible or short infrared photons per second and per square millimeter. And if you have a lens that is larger, you'll have more photons. And your single photon that you've sent out and like to detect its time of arrival has to compete against all these other background photons. makes it very hard. There are tricks, I'm not going into them, because what today is being done, for example, in all of your smartphones, is something else. Use more photons. So now I shift gears toward more photons. Let me talk about something that has already been mentioned. If you have bunches of photons, you can talk about their spectral distribution. And knowing about the spectral distribution lets you learn more about the objects you see, in particular in the food domain. So, if you know more about the distribution of where are there dips or where are there peaks in the spectra, you can find out more about what are you seeing. So this is an example from a company that is offering this small, portable, near-infrared spectrometer for technical people. You find here the sensitivity extends from the 900 to 1700 nanometer short infrared spectral range. And looking at that, they claim, oh, we know everything about the food we're looking at. Be careful with their claims. I know you can't read that, but it's incredible what they can see in the food. They can see, for example, antibiotics. That may be true, but at concentrations that are simply impossible. So the real point is not only specificity, it is also sensitivity. You need a very high dynamic range, and the question is, how useful is this technique if you have concentrations of the different constituents that vary a lot? I have my doubt, but still there is some use. For example, another company in Israel, they have the SIO diet sensor, because they can look at a scene and realize, oh, there is meat, and oh, there is ice cream. Ice cream has a lot of calories. So by just looking at your plate, they can estimate how many calories are these. And then they tell you, you should not eat all of your plate, or leave out the ice cream, eat only salads. I don't know how useful this is, how people react. The only thing I know is that SIO is offered by an Israeli company. They have now 100 employees. So there must be a need. Now, if you want to go to higher sensitivity and higher selectivity, what do? And the answer is, for example, the answer of Hamamatsu, what you need is an interferometer. And the preferred type is a Fourier transform interferometer. This sounds like something very big. You need an optical setup that is so complicated. You see how small it is? So this is the tip of a finger, and the actual device just needs a few 100 square or cubic microns. That's very small. And I've learned that devices like this will be in selected smartphones this Christmas. Watch this space. This is just 1 pixel, but it's the beginning. And the resolution you can achieve, this is called a Fabry-Perot interferometer, is below 1 nanometer. So the resolution is getting really good. The specificity is excellent. At the moment, people can cover, let's say, as we heard, indium gallium arsenide, which is the dominant detector used here, maximum 2.7 microns. What is coming with other types of semiconductors, this will go up to 10 microns. And perhaps some of you know the diagnostic window where the dips and valleys are particularly steep and high or low is between 3 and 10 microns. So this is a field to watch. It will come, it will allow a completely different, much deeper understanding of what do you see in a scene. Now, of course, I have to talk about time of arrival, time of flight techniques. Do you realize that depending on the application, different modulation schemes might be appropriate? The simplest one at least on paper, is you just emit a pulse of light. That's not so simple, because the pulse of light should be a few hundred picoseconds long. It should have instantaneous powers of watts or more. So you see, that's perhaps not so simple. But expensive equipment with very high resolution are making use of that. What you find much more often in low-cost solution if you have a sinusoidal modulation. What other people are employing, inspired by animals like the bat does not emit the beep. What the bat says is beep, 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 like in radar. So the bats are doing what radar is doing very successfully. They chirp their emitted light. That's not used yet extensively. I see some people doing research, may come. And all, of course, to reduce the effect of background light. That's the main problem to be addressed. And there is another main problem not many people appreciate, but if everybody has a 3D camera using time of flight, and everybody is using pulses, how can you discern between the different pulses? You can't! So what can you do? Well, most of you are mathematically trained. Use random numbers, or at least pseudo-random numbers. And these 3D cameras with binary pseudo-random number sequences, they are coming on the market now. This sounds very complicated. I'm surprised and quite cheered to tell you how cheap this has all become. Let me show you two examples. One you will have in your phones, because your smartphones, they know how far away your phone is from your ear. Time of flight techniques are being used for that. And of course, if it's in your smartphone, it must be dirt cheap. And it is. Let me show you how they did it. Since we are in Lyon here, so I'm going to show you the French solution, which actually is found in many smartphones. So ST Micro has a solution that looks like that. It's very small, a few millimeters, and inside, amazing thing, this is what you find inside. So you have a piece of silicon bonded to the contacts so that you can make contacts on the PCB. Everything for the detection, for the time discrimination, for the time to digital conversion, for the protocols to communicate is in this piece of silicon. In particular, the avalanche photodetector, which you see here, plus a driver for the light source. And the light source is just bumped on top, glued on top. It's a VCSEL, so vertical cavity surface emitting laser diode, and it's emitting light pulses. Now, light pulses are expensive. They don't use light pulses. What they use is they use light that is turned on and sharply turned off. So what you really measure is the time the current is turned off, and that gives you the time of arrival with a resolution of, let's say, 100 picoseconds. So that's good enough for this application. The amazing thing is the price. In volume, $1 for this complete time of flight module. Now, if you want a picture, it gets a bit more expensive, but still surprisingly low. This is a Swiss company, and Espros Photonics, they're also selling you chips. It's two-dimensional demodulator pixels with everything, including drivers for the VCSELs, on board. So what you need is only this chip, and you need a few LEDs, you're done. You can build a complete 3D camera. The resolution is amazing. They claim, down to 150 microns, time of flight. They're using modulated light, about 100 megahertz modulation. So, very simple calculation. Their precision with which they can determine the phase in the demodulation is of the order of 1 picosecond. I asked the owner of the company, what do you want for this chip? He said, if you buy them in volume, Peter, you can have them for $10. And that's really inexpensive. And you have a complete two-dimensional matrix. In each matrix, you know what is the distance with a resolution of 150 microns. So we've really come far. Now you ask me, for some of your applications, 100 microns of resolution is not good enough. I would like to go to 10. 1 microns. Can you do 0.1 micron? Oh, yes, I can. Let me show you how. And this has to do with the property of a light source. Many of you imagine a light source is doing that. It isn't. What it's doing that, and then it gets tired, it restarts. It looks like that, which means that any light source has a sort of a coherence length. Within this coherence length, you can build an interferometer. Okay, so this coherence length for different light sources is of the order of 15 microns if you have an LED. If you have a mercury vapor lamp, 30, 50 microns. If you go to diode lasers, tens of centimeters, a good helium neon laser, 60 centimeters, and a real good single mode diode laser is 100 meters. And if you want, if you have the cash, you can go to hundreds of kilometers with a single mode fiber laser. And since I don't have much time, I'm going to rush through these transparencies. This is used in an interferometer setup, really the interferometer setup that you've probably heard about at university. You use a coherent or partially coherent light source that is going through a half-silvered mirror, a beam splitter, to a reference mirror and back to detector, but also to a mirror to your object, back into the detector. And the only thing you measure with the detector is you measure, is there coherence or not? Okay, you want an image. I can give you an image. The only thing I change is I'm going to replace the single pixel with many pixels. All the rest is the same. What I can do with that is used, for example, by your ophthalmologist. He measures the distribution of the different layers in your retina with a resolution of 3 to 5 microns in all 3 dimensions. Now, the big advantage is you see also through diffusely scattering objects. So, what do you see when you see your finger? Essentially the surface. But more can be seen if you use these coherence, these OCT, optical coherence tomography techniques. This is a 3D image rotated of your fingertip. And you see the sweat glands. So this is, to my knowledge, one of the only possible ways that you can exclude all scattering, all fog, all additional optical properties, semi-opaque. You can look into the object. As long as a few photons come back, you see the 3D structure. How good this technique has become, let me show you a state-of-the-art, a flagship product of the company Heliotis. They have such an OCT system with 512 by 560 pixels and a height resolution of down to 1 nanometer, even getting better. Now, I'm coming to my last few slides. Again, I have to rush, although it's a fascinating topic because you can look around corners. And you can do it by an optical setup looking like that. You illuminate a scene by a laser. There is an occluder, a screen, so that the camera does not see behind the screen, but it can observe light that is reflected from a diffusing wall a first time by the hidden object, a second time, and a third time So if you know where is the light coming from and at what time, you can reconstruct the complete 3D image of what is behind the screen. And since you're all image processing people, I cannot resist the temptation to steal the minute to explain how it's done. Very simple. Okay, let's look at this point S on the object. So this point S will emit light in all different directions. Now, if the camera here sees light coming from this point here, so if you see it on the image sensor to the left, then you know, the time is so long, and therefore the object has this distance. Actually, the camera sees, and this is now this picture here, sees such distributions coming from one spot. So this is a hyperbola in this, what is the time of arrival as a function of a lateral distance. So you have from one spot a hyperbola. If you have many spots, you have a linear addition, a linear superposition of these hyperbola. And now I see a few eyes lighting up. So that's a linear problem. I can inverse it. You can, it's not very stable. Fortunately, you have also the direction of the light source you can play with. So, yes, you can reconstruct the image, and this is an example of what people have done, so they can look around corners and they see the shapes. Now, I come to my last slide, because these people said, it's actually true what we all suspected, what you have in our conference's announcement. If you have more properties of your photon measured, you can say more about the properties of the scene. You can say more than is possible with image processing. And to prove the point, the people came up with 3D representation of all these distance measurement technique shown here, where you can measure time if you want. You can measure the two-dimensional, actually that's two coordinates here, because in an image sensor you have two coordinates, and you can measure the angle of incidence, and all the techniques I presented to you can be found somewhere here. OCT is here, and what I just showed you is found here, 5D light transport. Now, the conclusion of the people were, if you have a higher dimensional representation, if you need more, if you measure more properties of the photon, you can really expand the horizons of image understanding beyond what is possible with image processing. So, in a summary slide, I hope you appreciate that in some applications you use a small camera, creating simple pictures, and you need a lot of image processing to understand. In other applications, you start with very complex optical setups, creating complex representations, but you only need a little bit of image processing. So, my parting words, may the wisdom be with you, that you can always discern what is the best approach, that you find the optimum compromise, and my second wish is, may you have many stimulating everyday experiences. Thank you.